All right, so we've introduced the sigma bond. It comes from in-phase or constructive overlap of a 1s orbital on hydrogen with an sp3 orbital on carbon. There are 4 of those, so we get 4 sigma bonds in methane. Similarly, there are going to be 4 antibonding orbitals in methane. I won't attempt to draw all of them. What I will do is show you what an antibonding orbital looks like. So in methane, an antibonding orbital associated with a CH bond is going to involve a node in between. So the dotted line there, the straight line there just indicates this is where the carbon-hydrogen sigma bond is. Here in gray is a dotted line that corresponds to the node, the place where the wave goes through 0. There's a lobe on this side on the hydrogen that mostly points away from the hydrogen. We'll give this orange wave function sign. There's a small lobe here on the carbon pointing towards the node. It is pink. You can tell that it should be because you go through 0. You go from a positive side to a negative side. There's another node at the carbon, which I don't typically draw, and then a larger lobe pointing backwards away from the carbon-hydrogen bond, and it is got to have the opposite color as the lobe on the other side. We call this antibonding orbital sigma star. The term sigma for a bond refers to a bond where you could take one atom on one side of the bond and twist it around and rotate it, and the bond wouldn't change. So can you see how if you took the hydrogen on the end of a carbon-hydrogen bond and twisted it around, the orbital would stay exactly the same as it was? That's called a cylindrically symmetrical orbital or bond, and we call it a sigma bond because of that. One important consequence in chemistry is that you can rotate around sigma bonds. So we would say that methane here has, if we were to draw the orbital energy level for methane, we would say that methane has 4 sigma bonding orbitals and 4 sigma star antibonding orbitals. The sigma bonding orbitals are lower in energy than our starting point, this dividing line between where the non-bonding orbitals tend to be. And each of those sigma bonds in methane is populated with 2 electrons. In this structure for methane, the lines mean 2 electrons shared between atoms. So 2, 4, I'll come back to what the wedge and the dash is, but for right now, just assume that they are bonds. 2, 4, 6, 8. So there are 8 electrons. We fill the 4 bonding orbitals with 2 electrons each, and the anti-bonding orbitals are all empty. And that's our picture of bonding in methane. Again, each orbital on carbon, each bond between carbon and hydrogen involves a filled bonding orbital and an empty antibonding orbital. Methane is stable because all of the antibonding orbitals are empty and all of the bonding orbitals are filled. Yes?
So the antibonding orbitals are just possibilities where the electron could be when something else is introduced?
That's right. The antibonding orbital is a place where an electron could go if it were promoted from a lower energy to a higher energy. So if we shot just the right wavelength of light at this molecule, we could excite an electron from a bonding orbital to an antibonding orbital, or another molecule could come in with its electrons and interact with methane, and the place it would be able to interact is those empty orbitals. Yes?
So is that what causes a bond to actually break then?
Yes.
When you put energy into it, put it into the antibody?
Exactly. This is what causes a bond to break. Either you add energy in the form of light to promote an electron to an antibonding orbital, and then that bond breaks, or you take another source of electrons and you dump them into the antibonding orbital and you cause that bond to break. Antibonding orbitals exist. They are places where electrons could go if you promoted them at a higher energy, or they are places where if you had extra electrons and dumped them into the molecule, that's where they would go. They're the next place on the list. This is now the origin of the octet rule. Who decided that 8 was the magic number? Well, It just so happens that because of the available orbitals that we've mixed together for methane, we only have 4 bonding orbitals. We have 4 antibonding orbitals. If I surrounded carbon with more than 8 electrons, I would populate antibonding orbitals, and that wouldn't be stable. So carbon only bonded to 4 things. And that's a rule you can learn and memorize, but now you know the reason why. Let's talk about these dashes and these wedges. 3-dimensional reasoning is really important for this class. As you develop this, you may need a molecular model set to help you out. I mentioned that in the syllabus. I don't recommend a particular version. Find one on Amazon that's cheap and with decent reviews, or some other vendor if you prefer to avoid adding to Bezos's trillions. In any case, you're going to need a little bit of help understanding molecular geometry. On a 2-dimensional surface, this is the best that we can do. But let me show you a structure of methane in 3D so you've got a picture of it. This is a program called Spartan. I don't know whether it's still available for iPad or not. I don't necessarily recommend getting it. It's like a $10 or $15 app, but it was a steal. That's a steal for a chemistry teacher. Here is methane. Notice that methane is tetrahedral. If we measured those bond angles, they would all be 109. I'm going to orient methane so that 2 of the carbon-hydrogen bonds are in the plane of the page. So I'm going to use the laser pointer here. This one vertically is in the plane of the screen. This one here pointing diagonally downward is in the plane of the screen. Then you have this one in the front and it's coming out at you. And then you have one in the back that you almost can't see, and it's pointing away from you. This is what we mean by tetrahedral geometry. To draw that on a 2-dimensional surface, and maybe let me orient it the way that it is on my paper. Remember, in the plane of the page, out at you, and then the one in the back that you can't really see pointing away from you. We're going to communicate that in 2 dimensions on a sheet of paper like this. This is the bond that's in the plane of the page. This is the bond that's also in the plane of the page. That angle is 109 degrees. This one, this wedge, is coming out at you, and then the dashed line is pointing away from you, all with 109 bond angles. You need to get used to drawing atoms that way. No more are we going to draw methane like this. Why? Because that drawing communicates that you think that all the bond angles are 90 degrees and that methane is flat, whereas it is not, and you now know that. Okay? All right. Let's talk about how we represent sigma bonds in organic molecules, and then we're going to talk about pi bonds. By the way, some of you are getting anxious looking at this thinking we haven't done any of that yet. Don't worry, if we don't get to it, put it in your backpack, we'll get to it next time, and then you'll turn it in, okay? We're going to be flexible, because sometimes we go slower or faster depending on how things work. All right. So it turns out that in methane, we've drawn this molecule where we've got the carbon and the hydrogen. The molecules we're going to be dealing with in this class are enormous, and it gets tedious to draw out all of the carbons and all of the hydrogens. So let me give you an example of how to draw a large organic molecule. We're going to use hexane, which is C6H, oh brother. Maggie, thank you. Now, I could draw it this way. There are many possible versions of hexane. Man, I should have chosen, will you let me choose, can I choose something smaller? I retrospectively choose something smaller. Not hexane, butane, all right? That's going to be much better. So I could draw butane like this. 4 carbons, bonds all in the plane of the page, hydrogens on either end in the plane of the page, and for each carbon in the middle, a wedge and a dash. A wedge and a dash, a wedge and a dash, and that is butane. Okay? Not so hard, but we have shorthand for doing this, and it's called the skeletal structure. And in the skeletal structure, you draw all the carbon-carbon bonds, and you omit the carbon-hydrogen bonds. You also don't write the C. You assume that there are carbons wherever lines meet, or end. And you try to imitate reasonable bond angles. So in butane, all of the CH and CC bonds should be 109 degrees away from each other. You can tell that because the carbon is bonded to 4 things. It should be tetrahedral and therefore sp3 hybridized. The skeletal version of butane is going to look like this. Not actually like that. I did one too many. Okay? Much easier, right? Less writing, less details. This is fully equivalent to this. When you look at that, you need to see the bonds that are implied but not shown. You need to look at that end of the line and say that is a CH3 group, and it's tetrahedral. You need to look at this vertex between the 2 lines and say that is a CH2 group. It's also tetrahedral. Yes?
So you do the skeletal system. What's the other one called? Where you do that?
Oh, what's the other one called? I don't know. Call it the dumb way, or no, call it the labor-intensive way. Couple of rules for skeletal structures. You can draw the hydrogens in if you want to. If you draw in the letter C, you must draw in all the hydrogens that are there. None of this. This is garbage. You draw this, and I will not throw my Apple Pencil because it might break. I will just sigh and look at you in a disappointed fashion, okay? Doesn't work on my kids either, but okay. In a skeletal structure, you assume that every carbon has enough hydrogens to give it a full octet or for it to be fully bonded. Okay? Questions about that? Okay. So, let's deal briefly with the kinds of bonds that heteroatoms can make in organic structures. What do I mean by heteroatoms? In organic chemistry, we care mostly about carbon or hydrogen. So heteroatoms are not carbon or hydrogen, and these bring interesting reactivity to a molecule. These would be often oxygen, nitrogen, or halides like fluoro, chloro, bromo, iodo. They might include sulfur or phosphorus. Now, oxygen comes with how many valence electrons? Good. So in a stable molecule, how many bonds does oxygen make? 2, right? So that it can get a full octet. So an example of a molecule like oxygen that's making 2 bonds would be water, where you have 2 lone pairs and 2 bonds. Okay? How about nitrogen? How many valence electrons does nitrogen have? 5, right? So nitrogen can form how many bonds? 3. It's got 5, basically 1 lone pair and then 3 other electrons. So this is the molecule ammonia. If you go through the same analysis that we went through for methane, for water, you would see that there are 2 sigma bonds. That means there's 2 sigma OH bonding orbitals. There are also 2 sigma star OH antibonding orbitals. I don't know why I drew 2 sigmas there. That's weird. These are empty. And then you've got two lone pairs. What's the deal with a lone pair? Go ahead.
It's a pair of valence electrons that aren't bonded to another, like they're not in between the nuclei, so they push the other two bonds away from them.
Okay, good. So the two lone pairs are just two pairs of electrons that are not involved in bonds. If we were to draw an energy diagram for water, and I were to put the two oxygen-hydrogen sigma bonding orbitals here, and they're both filled, and I put the two oxygen-hydrogen anti-bonding sigma star orbitals there, and they are empty, where would I put the lone pairs? Where should they show up? Should they be lower in energy than the sigma bonds, or should they be higher in energy than the sigma bonds? Higher, you're right. Good instincts. Why?
It's more like it's bait because when they're bonded, they're lower energy.
Right, bonding is always lower in energy. So if you're not involved in a bond, you're higher in energy than all the other electrons that are involved in a bond. This is a really important principle in this class. There's two lone pairs. They're about the energy. You remember that dotted line I used to draw? That's the energy of non-bonding orbitals. These are the LP, the lone pair electrons on water, okay? Just as a preview, if you had to look at water and say, which are the most reactive electrons in this molecule, which are they? Are they the ones in the sigma bonds, or are they the lone pairs? Lone pairs, absolutely every time, 100%. You're going to get used to doing that kind of thing with structures of molecules, looking at the structure, thinking through it, and saying which electrons are most reactive. Let's do the same for ammonia. How many sigma bonds does ammonia have? Okay, so that means I've got 3 sigma bonding orbitals with electrons in them. How many anti-bonding orbitals must there therefore be? Also 3. There's 3 anti-bonding orbitals, 1 for each bonding orbital. And then what am I missing? Lone pair, and it's got to be in the middle, higher in energy than the bonding orbitals, because bonding is stabilizing, and those electrons are not involved in a bond. We would say, by the way, that those are the most reactive electrons in ammonia. Okay, we are now ready. What a whirlwind. We are now ready to do question 1 of your quiz. So question 1 of your quiz is to draw the molecule CH3CH2OH, showing all the valence electrons and including lone pairs. So we're not going to do skeletal structure here. This is the one where you're going to do all the CH bonds. And I want correct dashes and wedges. Go. You guys need some mood music? Duel of the Fates from the Phantom Menace. Okay, if you've got something you're proud of, turn to somebody close to you, compare answers. Even if you're not proud of it, if you need a little bit of help. Okay, anybody feeling brave? We want to come forward and use the Apple Pencil of Destiny. What's your name, sir? Sam. Hey. Young Samwise DMG. Come forward. Well, go ahead and draw the structure of this molecule is ethanol, which students at other universities imbibe recklessly. Go ahead and give it a try.
Is it
Oh,
on?
you're on erase. So up at the top of the screen, there's a thing you can tap for like a pen. There you go. All right, you're good. Okay. Any comments or concerns from the audience? Everybody's like, I'm not going to say anything.
I just have a question.
Yeah.
For the lone pairs, do we have to do anything strange with the?
No, you can just do two dots. You don't necessarily need to circle them. And you try to imitate sort of geometry, but it doesn't matter that much for lone pairs. Just that you know that they're there. By the way, showing lone pairs, if I don't ask for them explicitly, showing them is optional. But you always got to know that they're there. Other hand, yeah.
Does it matter if you start the angle going up or going down as long as it?
Nope, does not matter whether you start the angle going up or down. And the reason for that is, what do we just learn about sigma bonds? You can rotate around them. So, Sam, I might have chosen, and maybe some of you chose to do this, I might have chosen to draw it this way. Or like this. And that would be okay too. Those two different shapes that we've drawn for this molecule, those are called conformations of the molecule. And the reason we can get there is because you can rotate, these little arrows indicate that we can spin around carbon-carbon bonds. So as long as you've got the correct geometry at each carbon, as long as it's tetrahedral, as long as the lone pairs are there, you've showed all the H's for each C, you're good to go. Any questions about that? All right, Sam's our hero for today. Thank you, Sam. All right, what I think we'll do with this quiz, by the way, is if we don't get to all the questions, I'm just going to cut them off and recycle them and use them next time. You'll still turn it in, and we'll have the TAs give you credit for what you've done, even if we don't get to all of it. Okay? Because I'm always wildly optimistic for what we're going to get to in a given day. Yesterday, there was a great big faculty meeting over in the JSB where they were talking about student success because the Lord really cares about you at his university. And anyway, there was a guy from the music department who was playing the hymns that we were singing. And on the last hymn, we were singing, "Help Me Teach with Inspiration." There was a key change between verses, and then there was another key change between verses. And it was wildly optimistic in terms of what my range was going to be for singing. So in similar ways, this may be wildly optimistic in terms of what we're going to get to. Okay. Now we need to talk about sp2 hybridization. Oh, before we move on, looking at ethanol, knowing what you know about bonds and lone pairs, what are the highest energy electrons in ethanol? Go ahead. Lone pairs on oxygen. Good. Bingo. That's really, really, really important. And we'll do this with other molecules in the future. Let's now talk about sp2 hybridization. And the best place to talk about this is to consider the molecule ethylene, which is C2H4. If we draw this molecule, its Lewis structure looks like this. And the shape of this molecule, each carbon, we'll talk about what this double bond means. Each carbon is surrounded by only three things. To keep electrons pairs maximally apart, the geometry of each carbon is trigonal planar, which means that all of the bond angles between carbon and hydrogen and between carbon and carbon are 120 degrees. Okay? Does that make sense? Have you heard what trigonal planar is? In fact, we've actually drawn this molecule in the correct shape. We don't need any dashes or wedges. All of the bonds that we've drawn there are in the plane of the page. Ethylene, C2H4, is flat. Okay? Now, let's talk about how we get flat geometry. And what sp2 hybridization means is we're going to take our alphabet of the 2s orbital, the 2py, and the 2pz orbitals. I'm going to erase the word node because you guys already know what that means. This is 2pz. We're going to mix two of the three p orbitals with the 2s orbital. We're going to mix those together using maths of molecular orbital theory that I will never ask you about. You mix three atomic orbitals together, you're going to get three new orbitals out. We're going to call them sp2 orbitals. The 2pz orbital we leave alone, unhybridized and unchanged. It just so happens that when you mix the 2s orbital with the 2px and the 2py, you get three sp2 orbitals, and if I were to draw where those orbitals are, they look in shape very similar to sp3 orbitals, but their orientation is different. If this is a carbon that is sp2 hybridized, one of the sp2 orbitals looks like this: a large lobe on one side of carbon, a node at carbon, a smaller lobe on the other side. And then 120 degrees away is another large lobe, and then on the other side, a smaller lobe with opposite wave function sign. And then pointing 120 degrees away from that is a third lobe, again, and then on the opposite side, a smaller lobe. All of these three orbitals are in the same plane. And the bond angles between them are all 120 degrees. I'm trying to emphasize somehow that these three sp2 orbitals are what we will call coplanar, meaning they occupy the same plane, by actually drawing out that plane as a parallelogram. Okay? Now, that's what we got by combining 2s with 2px and 2py. The plane that I have just drawn in gray is the xy plane. Still on that carbon and still unhybridized, I now need to erase this so I've got space, is the p orbital, the 2pz orbital that was on that carbon. So an sp2 hybridized carbon has three sp2 orbitals and one remaining unhybridized p orbital. The sp2 orbitals are all in the same plane, whereas the p orbital juts out above and below the plane. Does that make sense? that carbon is trigonal planar sp2 hybridized. Now let's talk about where the bonds come from. Looking at that carbon, where do you think, I'll need another structure of ethylene just because I want to keep those labels there, but I'm going to need more space. All right. Looking at ethylene, where do you think this carbon-hydrogen bond comes from? What orbital on hydrogen combines with what orbital on carbon to make that sigma bond? That was not rhetorical, so somebody can raise their hand and answer. Start with the one on hydrogen, that's easy. What atomic orbital on hydrogen is always involved in bonding with hydrogen? That's 1s, right? So that's 1s on hydrogen. Then what's the orbital on carbon that points in the right direction? Has to be sp2, right? Because like the CH bonds in ethylene, the sp2 orbitals are also oriented 120 degrees away from each other. So yeah, you get that bond from a 1s orbital on carbon and a 1s orbital on hydrogen and an sp2 orbital on carbon. Good. Same with all the other ones. Right? So we can account for all of the carbon-hydrogen bonds. We got 2 carbons. On each carbon, we check off 2 of the 3 sp2 orbitals. Questions about that? Yeah, go ahead.
So the 1s is acting on the hydrogen or it's acting on the bond between
The 1s is on the hydrogen. The sp2 is on the carbon. You bring them together end to end and they overlap. What that's going to look like, if this is the 1s orbital on hydrogen, and this is the sp2 orbital on carbon, what that's going to look like for our bonding orbital combination is like this. And if we were to sort of draw out the result, if you were to draw it out more simply, here's the position of the hydrogen, here's the position of the carbon. The sigma bonding orbital looks like this, where a lobe on the carbon envelops the entire hydrogen. And yeah. Okay, good. How about these 2 bonds here? One of them comes from overlap of the 2 sp2 orbitals on each carbon. So let's show you how that would work. Here's an sp2 orbital on the first carbon. Here's an sp2 orbital on the second carbon. We're going to bring them together with the same wave function sign. And that's going to be the sigma bonding orbital. This here over here was a carbon-hydrogen sigma bonding orbital. If we draw out what this actually looks like, a carbon-carbon sigma bonding orbital has a large lobe in between the 2 atoms, and then oppositely charged lobes pointing away from the space between the 2 atoms. And you can see that these are both sigma bonds, because if you took, these are each sigma bonds, if you took one on one side and twisted it relative to the other, there's no change in overlap. Okay? Both of these orbitals involve what I will call end-on-end overlap. End-on-end overlap leads to sigma bonds. Okay, so we've accounted for, I'll label them in blue, 2, 4, 6, 8, 10 electrons in ethylene. What we haven't done is accounted for that second bond between the 2 carbons. Now, if you think about an sp3 hybridized carbon, what atomic orbital on carbon haven't we accounted for yet? We already got all the sp3 ones, right? sp3 on carbon makes this bond, and this sigma bond. The sp3s, I'm sorry, I get confused. sp2 orbital on this carbon, one here, and one here. sp2 orbital on this carbon makes this sigma bond, and that sigma bond. In other words, we've accounted for each of the sp2 orbitals on each carbon. What's left over is the 2pz orbital on each carbon. Now, where is that orbital in space? How do you visualize it? If we're looking at if we're looking at our sp2 hybridized carbon here, notice that the plane of the sp2 orbitals is perpendicular to the p orbital. So tell me, in our drawing here, where the carbon hydrogen and carbon sigma bonds are all in the plane of this page, where is my pz orbital on this carbon? Go ahead. Yeah, one side of it would be coming out. Go ahead.
Is it the other double bonds?
Right. It is, we're going to get this from the other bond and the double bond exactly. And the p orbital, one side of it should be coming out at you like a wedge, and the other side should be going away from you like a dash. That's difficult to draw. One of the ways I do it is I just imagine what would a p orbital look like if I stared at it from the top. So, just put that as an eyeball, and in case you didn't know, it's the highly jaundiced and inflamed eyeball of a Sith Lord. Go watch Revenge of the Sith, Anakin as he shouts, "I hate you!" at Obi-Wan. That's what his eyes look like. So you're visualizing, this is what you say to me when you're studying for this class, visualizing that p orbital. It would look like a sort of circular lobe on top, and then in the back, almost where you couldn't see it, is the lobe on the other side. We'll go orange on the top, pink on the back. Okay? And that's the 2pz orbital on that carbon. Similarly, there's a 2pz orbital on the other carbon. And notice that they're not overlapping end on end, but they are side by side. I'm going to redraw this molecule just to help you see it. I'm going to put the plane of the page here as this parallelogram. Here is the carbon-carbon sigma bond, a carbon-hydrogen sigma bond coming out at you and going back. And then, so we're sort of looking at this molecule on its edge. Then the p orbital would be here and here below the plane, and here and there above and below the plane of the page, respectively. You see those two different views? Okay. This is called side-by-side overlap of 2pz orbitals. And this makes our second kind of covalent bond for the day. We've dealt with sigma bonds. When we get side-by-side overlap of 2pz orbitals, we get what is called a pi bond. Pi is the Greek letter for our Roman p, so it comes from p orbitals. We call it a pi bond. Similarly, S, the Greek letter sigma is our letter S. S is for single bond, maybe. Sigma bond is a single bond. Pi bond involves a side-by-side overlap of p orbitals. So just like we've done before for every sigma bond, there was a bonding orbital and an anti-bonding orbital. We're going to do the same for pi bonds. So a pi bond is going to have a filled pi bonding orbital. And if you want to draw what that filled pi bonding orbital looks like, I'll do the side view because that's maybe most convenient. We're looking at this. I'm no longer going to draw the parallelogram that represents the plane that we're looking at. A pi bond comes from side-by-side overlap of those p orbitals. There are two lobes above and below the plane of the sigma bonds sort of bleed into each other, and you end up with this, what people have called hot dog bun shape, that is above and below the plane of the page. Notice that they're in this pi bonding orbital. We'll call this the pi bonding orbital, already wrote that. There is no node between the nuclei. So that electrons in this orbital would tend to share the space between the two nuclei and pull the two nuclei closer together. However, notice that this bond has different geometry than a sigma bond. Notice that in a sigma bond, like the ones shown here, electrons in that orbital spend their time along the straight line that's in between those two nuclei. Whereas electrons in a pi bond are not going to be along a straight line between the two nuclei. They're going to be hovering above and below. Okay, make a prediction. Which do you think is higher in energy, a sigma bond or a pi bond? Pi, good instincts. Why? Okay, so we're thinking about how being along the straight line between the nuclei. Yes, proximity to the nucleus equals lower in energy. In the same way that my potential energy here on the first floor of the Benson building, where I'm closer to the center of the earth, is lower than it is when I'm in my office with my Star Wars Legos on the fourth floor of the Benson building, where I'm farther away from the center of the earth. Farther away you are from the nuclei, the higher you are in energy. So a pi, and yes, you can come see my Star Wars Legos, UCS Millennium Falcon, baby, it's awesome, come take a look. In any case, the farther away you are from the nucleus, the higher in energy you are. So pi bonding orbitals are higher in energy than sigma bonding orbitals. Second consequence, do you remember how I told you how sigma bonding orbitals, you could take one on either side and twist them and nothing happened? What do you suppose happens to a pi bond if I twist it? The thing that makes the pi bond is perfect side-by-side overlap of those orbitals with the same wave function sign. If I rotate one side, they're no longer overlapping side by side. And one rule that you don't totally need to know for organic chemistry, but it's useful, is that when orbitals are perpendicular to each other, they can't bond with each other. It's only side by side or end on end overlap that makes bonds. So a pi bond, because rotating would cause the orbitals to stop overlapping, rotating actually breaks the pi bond. So we don't rotate around carbon-carbon pi bonds. That's an important fact that actually plays a role in how you and I see. We're not yet ready to talk about that, but we will soon. But I want you to remember that rotation is restricted, meaning it can't happen around pi bonds, because doing so would break the pi bond. One other point of clarification, a double bond consists of two things, a sigma bond and a pi bond. You may have heard in the past, double bonds are stronger than single bonds. That is true, and now you're trying to resolve that with what I just told you about pi bonds being higher in energy, less stable than sigma bonds. A double bond consists of both sigma and pi. Pi is less stable than sigma. Together, though, they're stronger than a sigma bond. Does that make sense? Okay. I think that just about does it. Put your name on the quiz. We got to one question. Yes. Put your name on the quiz. Turn it in up here on your way out. I will see you tomorrow. If you have questions, I'll be up in my office this afternoon.